Hey guys, welcome back. Today we're going to talk about our acceleration lab that hopefully you watched and you were able to get all of the numbers here that we collected together. Um, in a minute here, I'm going to fast forward time and I'm going to write all these numbers in. But yeah, we're gonna analyze the data that we collected, finding the velocity and acceleration, and perhaps we will go into finding the graphs and kind of starting the graphs off for you. I'm not going to go through the entire thing. I'm definitely not going to do these questions for you. Those will be for you, kind of what you learned. Show me how smart you are. But we'll go ahead and start the acceleration graph, the velocity graph, and the position time graph, as well as fill in this table here. Okay. So let me fast forward time here for you. Okay, here we are into the future. Fast forwarded time there for you. And now what we're going to do is we're going to try to find the average position, right? We're finding the position average between the three trials, trial 1, 2, and 3. Okay. Now, remember, in order to find the average of three things, which is what we're going to do here, we're going to add up those three things and divide by 3. So 1.3. Oops, I forgot to put a plus there. 1.3. Okay, so notice I put 1.4 plus 1.0 plus 1.3. And now I want to find the average of them. Well, sometimes be careful, if you're using one of these calculators at least, not to hit divide 3 at the end, because then we're going to get this weird number 2.8. Well, 2.8 is definitely not in the middle of those. So I always show my students that just as something to be aware of. What I would do instead is type it out 1.4 plus 1.0 plus 1.3, hit enter, and then we get 3.7. Now we're going to take that and divide by 3. Okay, we get 1.233. And we want to round to, looks like 2 digits, right? 2 significant digits there, which is 1.2. Okay, and our unit, meters. All right, if we average out 3.6, 2.8, and 3.4, remember, let's add them up. 3.6 plus 2.8 plus 3.4. 9.8 divide 3. 3.26. Notice that 6 is going to round this up to 3.3. Okay, now I'm just going to quickly fill these rest of them in. If we get 5.6, if we average those, we get 9.1 if we average those. And that's all I'll do for you. You can figure out the rest. There's only 4 more. I did 4. You do 4. Okay, so let's keep going. Change in time. Well, what's the change in time? I went from 0 seconds to 5 seconds. What's that change? Well, that change is 5 seconds. Okay, from 5 to 10, we also have a change of 5 seconds. I think you may get the idea by now. Okay. All these are going to be 5 seconds, except for this very last one, which is by itself, so 0 seconds. Okay, at 0 seconds, well, we're not going to have a change in position. This really doesn't even apply 0 seconds, so we'll just put a line through that one. But we do know what our velocity was whenever it was stopped, right? At the very end, it was stopped. What was our velocity? You say 0. Yeah, that's right. 0 meters per second, because it was not moving, was it? Very good. Change in position. At least I assume that you got it. Hopefully you did. We'll say you did. 1.2. Started at 0, ended at 1.2. What's our change in position? 1.2 minus 0 is 1.2. Okay. Same thing here. 1.2 to 3.3. If we subtract 3.3 minus 1.2, we get 2.1 meters. Next, we get 2.3 and then 3.5. Okay. Now let's find our velocity. Well, our velocity, how do we find that? What's the formula? We remember that our formula from the notes the other week is change in position over change in time. There's our velocity formula. So using that, we're going to have this column, change in position, divided by this column on the left, change in time. 1.2 divide 5. 1.2 divided by 5. 0.24. Well, Notice that we only had one sig fig here with the 5. So I'm going to put 0.2, right? That 4 is going to round it down to 0.2. Next one, 2.1. 2.1 divided by 5. What do we get? 0.4. 2.3 divided by 5. 0.46. Notice that 6 is going to round that up to a 0.5 meters per second. And the last one, if we did it 3.5 over 5, we get 0.7. Okay. Of course, you guys will do the rest. Now let's keep going. Okay, what's our velocity at time 0? Our velocity, whenever we started, was 0. Okay, now here's what we're doing here. We're taking the average velocity between these two, and we're saying at 2.5, we're assigning it a time value. At 2.5 seconds, more or less, our velocity was, well, what? Between 0 and 0.2, if we average them, we get 0.1. 0.1. Okay. 0.2 and 0.4, we get 0.3. Between 0.4 and 0.5, we get 0. We'll put 45 here, just to say it's halfway between them. 0.6 is between 0.5 and 0.7. Okay. Those are all meters per second. Those are velocities. If we were to have to guesstimate, okay, more or less estimate the speed that it was going at each of those times, we'd say it was this. Now then, change in time. Okay, so change in time between 0 seconds and 2.5 seconds. Well, the change in time would be 2.5 seconds. Between 2.5 and 5 is the same. And then we go from 5 to 10. Well, that's 5 seconds. And then we go from 10 to 15. Another 5 seconds. Right? Okay, so let's keep going. Now, what we do next is we're trying to find the change in velocity between these 2 points. Our velocity here was 0.1 and our velocity here was 0. What's that change? Change in velocity is 0.1 minus 0. So we get 0.1. Next one, we get 0.3 minus 0.1. That's simple, 0.2. 0.45 minus 0.3. Looks like we get 0.15. 0.6 minus 0.45, we get another 0.15. And you get the gist of it. Okay? Now, we are tasked with finding the acceleration. But first, I think I'm going to give you guys one more row just as a bonus for watching, I guess. Let me fast forward time while I fill in that bottom row. All right, here we are in fast forwarded time. Got you guys this next row down here. Now we're going to find the acceleration. What's the formula for acceleration? Well, remember that acceleration is change in velocity over the change in time. Hopefully you learned that from the notes. Whatever day before this you watched them. And here we go. Acceleration, change in velocity, this column, divided by change in time, this column. Let's start off. 0.1, or I'm sorry, I'll put 0.1 so you can see I'm typing that number. Divide by 2.5, which is our time, and we get 0.04. That's meters per second squared. Next one, 0.2 divided by 2.5. 0.08 meters per second squared. 0.15 divided by 5. 0.03. I think this one's going to be safe to say it's the same. And then we have 0.2 divided by 5. Last one is 0.04. Okay, so you notice most of these are all more or less the same. Okay. So you'll keep going. Remember that eventually this thing is going to start slowing down. Okay. Right now, so far, it's been picking up speed. Notice our velocity has been increasing. Eventually, our velocity is going to stop increasing and it's going to start decreasing. It's going to go from maybe 0.8 to 0.7, 0.5, 0.3, 0.1, and then 0, right? It's going to slow down. Well, if you have a slowing down velocity, that means your change in velocity is actually going to be negative. So if you get a negative number, you're doing it right. Okay. Whenever you start to get smaller and smaller numbers here. Therefore, your acceleration should also be negative. Okay. You'll see that as you continue to go into calculating those values. Let's go ahead and go to the graphs. Okay. Well, on this first graph, we've got position versus time. Okay. So you'll come up with your scaling. I'm going to go ahead and fast forward time to come up with whatever scaling I decide to do. But kind of choose, right, something that makes sense. Well, you started at 0 and you ended at 16.9. So maybe I'll go from 0 to 20 all the way at the top. Remember that position? It's going to be your y value. And your time is going to be your x-axis. Well, our time ended at what, 40 seconds? So I think 40 should be over here. That means 0 is going to be over here, obviously. And we're going to count the lines. I'm going to fast forward time so I can tell you how many lines there are here. All right, here we are in fast forward time. I don't really know what I said last, but I think I've got the scaling here. I figured out that I'm going to do, I don't know what you, whatever you pick is fine, but I chose to go on the time scale. Since we went from 0 to 40, I chose every third line will be 5 seconds. Okay, which are the time intervals that we've got here on, of course, our data sheet, right? So notice here at 0 seconds, we start at 0 meters. I'm going to go ahead and start inputting the dots, I guess you could say. Okay, so we started at 0 seconds at 0 meters. At 5 seconds, how far were we? Well, notice here we are at 1.2 meters. Okay, 1. Notice on my position, every line is 1 meter. And it actually ended up perfectly going all the way up to 20. Okay, 1.2 right there. At 10 seconds, I'm only going to go up to 25 seconds. At 10 seconds, 3.3. 3.3. So they're at 3 and maybe a third of the way up to the next line. At 15, we're at 5.6. A little bit above halfway. There it is. At 20, we're at 9.1. And 25, we're at 13.6. Just right there. What you could do is kind of try to connect the dots, right? Just like we learned in kindergarten. I always find that fun. There it is, connecting the dots. Mine looks rough. Hopefully yours looks better. Let's go ahead and continue on, guys. There's our position versus time graph. Okay, I started it. You finish it. It's gonna be kind of neat. It should maybe like taper off a little bit here. Okay, but we will see. Only time will tell. Let's go on to the velocity versus time graph. Okay, and I'll kind of take you through my thinking process whenever we do the graphing section. Okay, remember velocity is going to be y-axis. Hopefully I spelled that right. And time is on our x-axis. Velocity y, time is x. 0, 0. Well, the time that we went up to was, what, 40 seconds, right? So 5, 10, 15, 20, 25, 30, 35, and 40. So our time doesn't need to change, right? It can keep the same keep the same table that you did last time. Now our velocity is where we're going to kind of think about what we want to do there. Well, let's see. We started at 0, and it never really got up past 1 meter per second, did it? Maybe it does. I don't know. Maybe these values right here, it goes past 1 meter per second. I don't know. But I'm going to assume that it stays more or less around 1. And I'm going to go with every line being 0.1. So every line is a tenth of a meter per second. Okay. 0.2, 6, 7, 8, 9, and 1.0, 0.0. Great fun watching me do this, huh? All right, there it is. So I'm going to input the values for our velocity, and it looks like our velocity at 0 seconds. Oops, look at that. We got a 2.5 seconds. Okay, at 0 seconds, we were at 0 meters. So we'll put a dot there. Okay. Oh, you're also going to have a velocity at 37.5. Blink. Okay, 2.5. It looks like our velocity we said was 0.1. So right there. Boom. Our velocity at 5 seconds was 0.3. Boom. Put that dot right there. So far, it's looking a lot like our position time. Strange. At 10 seconds, we were at 0.45, which is halfway in between 0.4 and 0.5. At 15 seconds, we were at 0.6. Okay. At 20 seconds, we're at 0.8. And I will connect the dots. I think this is going to be more or less a line of best fit, though, right? All right. Okay, so looks like it's more or less linear, right? Compared to our position time, where we kind of see almost an increase in our slope, getting steeper. Whereas this one's kind of like a straight line across. Okay, now having fun yet? Let's go over to acceleration, which is the very last graph, which means you're almost done. Okay, acceleration time. Acceleration, what's our unit? It's meters per second squared. Okay, 0, 0, 5, 10, 15, 20. Oh, don't forget the 2.5. 25, 30, 35, and 40. Okay, our acceleration looks like anywhere between 0.04 and 0.08. So I'll go 0.01, 0.02, 0.09, 0.10. Okay. More or less right there. I don't know if it's ever going to go above 0.1 meter per second squared. If it does, I would just continue that up. I left room for it. Now we get to graph. Exciting stuff. Okay, at 0 seconds, I think our acceleration, we could say safely that it was 0, right? Because at 0 seconds, it wasn't accelerating. It started off neutral. Then we released it. It started off first going 0.04 meters per second squared as an acceleration. So instantly kind of like jumps up, right? And then at 5 seconds, 0.08. At 10 seconds, 0.03. And then it stays at 0.03. At 15 seconds. And really that's 0.03 is between 10 and 15 seconds. So I'll kind of like, yeah, sure. Between there, it's there. Between 5 and 10 should be there. I'll put a bigger dots because I may have goofed up there. Sorry about that, guys. Between 2.5 and 5 should be there. And between 0 and 2.5 should be about there. I'll go back and I'll fix. It looks all sorts of goofy right now. At 15 seconds, what are we at? Between 5 and 10 was 0.03. Between 10 and 15 was 0.03. It's right there. Between 15 and 20 is 0.04. 15 and 20, 0.04. So this one, I think mainly because we picked our scaling to be so small, that might have been a bad idea. But that's all right. I think my scaling that I chose for this one is not really ideal. We should have picked between 0 and 0.1. And then we would have seen that it's more or less, our acceleration should be kind of like a flat line. But right here, maybe it looks like it had a kickstart at the beginning, and then it kind of gradually accelerating, right? But since our numbers are so tiny, 0.01, 0.02, 0.03, right? That means that it's accelerating at such a small pace that any fluctuation is going to be very noticeable with this scaling. So I would probably change my scaling to be from 0 to, I don't know, to 0.1, right? And then it would just stay in that first line all the way across. But I didn't. Something else to consider is that eventually your acceleration is going to be negative, and I didn't take that into account. Oops. Let's go ahead and scrap this then. Sorry, guys. We'll keep the time. Time doesn't change. Scratch it all off. Okay. So here's what I'm going to do instead. This is going to be 0. This is going to be 0.1 right here. This is going to be negative 0.1 right here. Okay. So if I was to plot those things back, our first point would be right around 0.04, which is like right there. Then I've got 0.8, which is like right there. And then I've got 0.03, which is like right there. Another 0.03, which is like right there. And a 0.04, which is like right there. Okay, now we can start connecting the lines and seeing that, yeah, really it's just a horizontal line. Okay, and then it might go negative, might dip down and go negative for a minute. Okay, so finish out that. Good luck, guys. Hopefully you can figure it out on the whatever device you're using. But we'll see you next time.